Most of it were published here, and a long paper in PRB will come out soon. So the motivation of this work can be summarized here. So if we have a topological defect, such as dislocation or a vortex, the question is, can we make it unstable if we drive it with a strong force? So, for example, if you have a dislocation, you apply stress and you move it along the crystal, or you have the edge dislocation, or the screw dislocation, or you have a superconducting vortex. They're both topological defects, and topological defects have a quantized winding number, and that winding number protects this defect so that if we want to destroy it, then we have to spend the energy which is proportional to the area of the system. So for dislocation, for example, if we want to eliminate a dislocation, we have to push two parts of crystals to merge them here, so we have to spend the energy proportional basically to this area, which is macroscopic. That's why the whole idea of making topological defects sounds silly, because if we make it unstable, it disappears. But to disappear the defect, we have to spend macroscopic energy. So how can it be? Well, what I'm going to show you is another possibility than when we actually, instead of eliminating this defect, a moving defect can generate pairs of opposite polarity of this defect so that it can eventually destroy the long-range order. So in other words, we have one topological defect, and we can drive it hard, and this topological defect starts producing pairs, and then eventually the long-range order will be destroyed. And I'm going to show it to you using Josephson vortex as an example. First of all, because Josephson vortex is well studied, we know everything about Josephson vortices and how to describe them. So if you start from the conventional Josephson vortex, so you have a Josephson junction here, and the tunneling current going across the Josephson junction. We have a Josephson vortex, which is a long loop along the junction, and it's described by the Sine-Gordon equation here, which has capacitance currents, resistive currents here, currents around the junction, and this is a Josephson current going across. And this equation has a well-known solution, 2 pi kink, and that 2 pi kink describes a Josephson vortex in which the phase changes by 2 pi, and the magnetic field has this bell-shaped form, and the size of this vortex is the so-called Josephson penetration depth. And the Josephson penetration depth is roughly square root of psi lambda, coherence length, London penetration depth, and the ratio of the pairing current density in the bulk and the critical current along the junction. So it's large. So typically along Josephson junctions, low GC Josephson junctions have Josephson penetration depth larger than London penetration depth. So this vortex is well known. It is stable, and we know that we can move it with current. And no matter what we do with this vortex, the velocity of this vortex is always smaller than the so-called Swihart velocity, which is some fraction of the speed of light, so the thickness of the junction, and this is dielectric constant. So as the velocity increases, Josephson vortex for low dissipation shrinks due to Lorentz contraction here. For overdamped limit, it expands. It's all well known. Now, is this correct? Well, generally, we have to take into account more general equation, which takes into account non-locality of London electrodynamics. And this is the most general form of the equation for the phase difference on the junction. And it has this integral term, which decreases on the scale of the London penetration depth. So how we get this, how we can reduce that to the Sine-Gordon equation? Well, if my vortex is large, the scale of variation of the phase difference is large, so I can simply replace this Bessel function with the delta function, then I kill this integral, I go back to the Sine-Gordon equation. And that gives a local relation between the phase and the magnetic field. So is this a standard procedure? But is this procedure missing something? And what I'm going to show you, it does miss a lot of things. So, and what it misses Cherenkov radiation of vortices. So what is Cherenkov radiation? If we have any object which moves faster than, if it moves faster than the phase velocity of electromagnetic waves in a junction, it'll radiate. So using sine-Gordon equation, we can calculate the phase velocity. So by linearizing it like this, so calculating the frequency divided by the k vector, and that's what we get. Now, if we plot this, we get this blue line. The phase velocity is a function of the wave number, and you can see that for all wave numbers, this phase velocity is always larger than the Swihart velocity, and because vortices can't move faster, it's always stable. However, if we take a more general relation like this, do the same. So now, instead of this unity, we have this square root, which is nothing but the Fourier transform of the Bessel function. Now, this thing depends on k. And then, instead of this blue line, we have this red line for large k numbers. So now this red line goes under the Swihart velocity. So if my vortex velocity is somewhere here, those electromagnetic waves with k numbers around here will be radiated. So now we have Cherenkov radiation, but I'd like to emphasize that I don't assume anything about the Josephson junction here. I'm simply using more general relation from which this was derived. So I can estimate the characteristic wavelengths of this Cherenkov radiation if my vortex velocity is close to the Swihart, and then I get that the characteristic wavelength is the square root of lambda and lambda j. So it is smaller than lambda j, but can be actually larger than lambda. So let's try to understand what happens if we drive the vortex, which is described by this more general relation. So here's what happens. So if I have a static vortex here, so you have the 2 pi kink, now you have a moving vortex, and you can see the trailing tail of Cherenkov wave behind the vortex. As I increase the velocity, this amplitude increases. And then there is a critical velocity at which this peak reaches the critical value, and then I start generating vortex and anti-vortex pairs here. So if I increase velocity a little bit from here, I start generating expanding phase pile. So I generate the pairs, they move apart, split again, and so on. They keep generating vortex and anti-vortex pairs. So why it happens? Simply because I have this region behind the vortex, which is in a pi state. So the phase here is in the region of phases where Josephson junction is unstable. So as I increase the velocity, this region expands this way and that way, forming the critical nucleus, which then becomes unstable. And that is the seed of this vortex and anti-vortex pairs. So then I have cascade of vortex and anti-vortex pairs. Let me show you what it looks like in life. So we start with the Josephson vortex, in which the Josephson penetration depth is 10 times larger than lambda. So it's a classical Josephson limit. So this is a damping constant, this is current. So now you see it moves, and it forms the trailing tail of Cherenkov behind it. Okay? So then we increase current a little bit, and you can see that the amplitude increases. Now we increase current again, and then what happens is this. So you start generating cascade of these pairs, and they don't stop if we have infinite junction. So there are lots of movies available here. So we check that in all different geometries for the bulk Josephson junction here in the local limit when Josephson penetration depth is large, non-local limit, and with Josephson penetration depth is actually larger than, smaller than the London penetration depth. The film edge junction, the thin film overlap junction, they're all different because you have different kernels in this integral. So they all behave very similarly. You have the critical velocity above which it starts generating pairs. So then you can calculate the VI characteristics, and you see two distinct regions. First, at small velocities, you're limited by the viscous drag, the ohmic drag. As velocity increases, it starts radiating more and more, and then here, from here to here, you have radiation friction, just because you radiate electromagnetic waves. And then there are endpoints where it becomes unstable. So this is for different geometries again. And you can see that actually this can happen at currents which are significantly lower than the Josephson critical current density. So here it's about 0.4 or 0.6, but in any cases it's below the Josephson tunneling current. And this is non-thermal mechanism of destruction of phase coherence in Josephson junctions. So actually, it's very similar to what is known as shear crack propagation or elastic twin, when you have pileup of dislocations of opposite polarities, and when you apply stress, they start moving this way, and you form a crack. And interestingly, this crack is described by dynamic piles equation, which is shown here, which is nothing but the non-local limit of the Josephson, this integral equation for the Josephson junction I showed you before. So then we can go back to the case of extreme non-locality in which the London penetration depth or the screening length is larger than the Josephson penetration depth. And that actually happens in a pretty wide range of critical currents. This is Ginzburg-Landau parameter. This is the thickness of the film. And then in this limit, this integral equation simplifies to the Piles form. It becomes exactly the Piles equation. And that defines the so-called Abrikosov-Josephson vortex. And this is Abrikosov-Josephson vortex core length, L, lambda j squared divided by lambda. There is an exact solution of this given here. So it describes me a driven Abrikosov-Josephson vortex. And the current streamlines are shown here. So this is Abrikosov vortex with a round core. Then if you decrease the critical current density across the junction, it disappears. It becomes a phase core of length L here. And this part is just given, well, it's slightly stretched, but it's just the screening currents flowing around the junction. And interestingly, there is an exact solution which describes a moving vortex in an overdamped limit. And from here, you can see that as the vortex moves faster, beta is the critical current divided by critical current density, it expands. These vortices have been observed in many systems, in transport measurements, then the STM and other systems. So this has been established by many experiments. Now, obviously, this infinite junction is a simplification because all junctions have finite length. And the question is, what happens if you have a junction with finite length? Then you have two in addition to the Cherenkov radiation, you have what's called Bremsstrahlung, which is nothing but the radiation of a charge with the velocity which depends on time. So if your vortex accelerate and decelerate, it radiates. So now we have two mechanisms of radiation, one coming from Cherenkov radiation, the other one coming from acceleration, deceleration of the vortex, and that is because this vortex is attracted to the edges of the junction the same way vortices are attracted to the edges due to images. So when the vortex enters and exits, its velocity changes, and that would radiate in addition to the Cherenkov radiation. So in this case, we have another effect. We have a dynamic transition of a moving vortex into phase slips. So when the vortex expands and the length of the vortex becomes of the order of the length of the junction, the vortex becomes a phase slip, and this transition can be actually calculated analytically. I'm going to show you in a minute. So let's consider the AG vortex in a thin film in a non-local limit. So then we can neglect the longness screening, and then the vortex can be actually viewed in the way shown here. So if I put my vortex here, and it has current streamlines, these current streamlines are as if I have a fictitious Abrikosov vortex sitting here, which produces current streamlines in the upper half plane, and to get currents in the lower half plane, I have to put the fictitious Abrikosov vortex there. Okay? So as a resulting current distribution has no singularities, and that is the AG vortex. So if I don't have any, or screening is weak, I can reduce London equation to Laplace equation and use the theory of complex functions to solve this exactly. So I can introduce a complex potential. This is a phase. This is a stream function. Introduce a current density. So my problem now reduces to finding two analytical functions with pole here and here, such that I satisfy the boundary condition of current continuity on a Josephson junction. So as I said, turns out that the analytical function which satisfies this property is nothing but the complex potential of Abrikosov vortex in the film. So now I have two Abrikosov vortices here and here with a point course, and now I want to merge them to form AG vortex here. So I open a textbook and I find complex potential which has a pole in the infinite strip. So here it is. From here I can calculate the phase difference, and that will be the phase difference in my AG vortex. Now it has the position of the vortex along the junction, U. Now L is the distance of this fictitious vortex from the junction, which defines me the core length, and chi is simply coming from the external current. So I can plot it here. You can see it's a kink, but it's not a 2 pi kink. It actually has the phase difference is smaller than 2 pi, and that is because vortex in the film has reduced flux quantum. So to ensure the quantization of fluxoid, I have to include this integral, the line integral of circulating currents, which are non-zero here because the width is of the order of the screening length here. So it turns out that the conditions of current continuity give me the set of three differential equations for chi, which is nothing but the equation for a point contact. And then I have two couple equations for the position of the vortex and the core length. So these differential equations, couple differential equations, describe me nonlinear dynamics of my vortex for any time-dependent current in the overdamped limit only. It ignores all radiation effects here because they're suppressed by dissipation. So now let's look at this equation and assume that you have stationary vortex and see under what conditions this vortex can exist. So we can find a place where vortex would be in unstable equilibrium, and then see what solutions we can get from the condition that this is zero. You have both real and imaginary parts. And gives you two conditions here. So a real part gives you this, the position of unstable equilibrium as a function of current. When current is zero, vortex is sitting in the middle of the junction. If current is non-zero, it's pushed to one of the edges, and that defines the position. Another one gives me the size of the core. Now here you can see that tanh is always smaller than 1, and that can be either smaller than 1 or larger than 1. So the vortex solution only exists if this is smaller than 1, and that tells me that the vortex solution exists only if the width of the junction is larger than the critical length. If it's shorter than the critical length, vortex solution no longer exists. It becomes a phase slip. It's somewhat similar to what Likharev did long ago for Abrikosov vortices. It's called core explosion transition. If you put Abrikosov vortice in the middle of the film and you start decreasing the film, you find that below the critical width of the film, the vortex solution disappears, it becomes a facelift. So here you can actually get it analytically, and the critical length is nothing but the AJ core length times pi. As you increase current, the critical length increases. So that suggests if I start driving these vortices, they start expanding, and I have a dynamic facelift transition at higher currents. So we did that. We performed lots of numerical simulations of this for non-local Josephson junction. So in which case, the integral equation looks like this. So that was solved numerically for different damping parameters and different currents. Let me show you some results. In the overdamped junction, you can see here the vortex. So this is the phase difference as a function of time. So the vortex enters here, moves across the junction, comes out here, then the next one comes in, and so on. Now, if I take a snapshot of the vortex profile in the middle of the junction, I get these things. So this is the case of current close to the critical. As I increase the current, you can see that it expands. So as the current increases, vortex simply turns to the facelift, simply because overdamped vortex expands as it moves faster. Now, if you go to a vortex with a weaker dissipation, I can see first signs of radiation. So here's my vortex comes in, and you can see that you have the trailing tail of radiation behind it. You can see a little hump here. So then it moves and exits, and then entire vortex enters from the other side, moves this way, and so on. And as I increase the current, I form standing waves, which are shown here for different times. And as I keep increasing my current, the amplitude of standing waves decreases, and it simply becomes a phase slip in which the phase increases nearly linearly with time. So if I go to even smaller dissipation, 0.7, now you can see that the vortex enters, and then it produces a pair. So here's my vortex. It's entering the junction, moving inside, and then halfway it produces a vortex entire vortex pair, similar to what I showed before. And so that is the instability I was talking about. So we did lots of other things. For example, we calculated interaction of this vortex with pinning center. So if you put a pinning center in the middle, a vortex can enter, hit the pinning center. It can produce a pair of vortex entire vortex. You can see that it actually passes the defect, leaving behind expanding vortex entire vortex pairs. VI characteristics were also calculated. So overdamped limit is very simple. It's non-hysteretic, goes up and down. So you have a transition to the phase slip somewhere here. As dissipation decreases, the Josephson junction becomes hysteretic. You see these little steps which give you the number of vortices in the junction. As I reverse the current, you see hysteretic behavior, and the hysteresis becomes wider as the dissipation decreases. And here, once my vortex enters the junction, it becomes unstable, generates lots of pairs. The whole junction becomes basically normal. As I go back on current, now I can produce lots of vortices in this stepwise manner. And then finally, around here, all vortices disappear, and I go back to the superconducting state. So the summary, non-locality can produce lots of interesting effects. For example, it gives you Cherenkov instability of driven vortices. There are lots of analogies with crack propagation, magnetic domains, and so on. And that is a new mechanism of destruction of long-range order by a single topological defect, which is driven by a strong force. The effect is most pronounced in underdamped SIS junctions, but in a junction of finite length, actually you don't even need very weak dissipation, because now you have radiation due to acceleration, deceleration of vortices. And In final junctions, you can have also dynamic transition of the vortice interface slips. Thank you.
Thank you very much.